Okay, so in this video we're going to talk about geometric series. Okay, so what's a geometric series? Well, it's a sum. And one example of a geometric series is this. And I'll just say plus dot 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 to say it keeps going on forever and ever in this pattern. But what is this pattern? Well, this pattern starts with 1/3. And then we add to that 1/6, then we add to that 1/12, 1/24. How do we get each subsequent term from the previous one? Well, you can see to get from 1/3 to a 6, we multiply by a half. To get from 1/6 to 1/12, we multiply by a half again, and so on. We keep multiplying by a half to get to each subsequent term from the previous one, and that is the hallmark sign of a geometric series. So a geometric series, it's just a sum of terms where the ratio between the successive terms, right? That's what we were just looking at. We were looking at successive terms. And the ratio of 1/6 to 1/3, the ratio of 1/12 to 1/6, the ratio of 1/24 to 1/12. In this case, all those ratios are a half. In general, the ratio just has to be a constant. Okay, so here that constant was a half, but it could be anything. Okay, and there's kind of a general form that the geometric series falls into, and it's where you start with some number a, and then you have the next term is a times that common ratio r. In this case, it was a half, plus a times r squared, plus a times r cubed, and so on. So you can see each term is the previous term times r, and some people call this a the coefficient of the geometric series, and people call this r the common ratio. Okay, because it's the ratio between successive terms and it's common to all successive terms. So in our example up here, a would be 1/3, okay, and the common ratio would be 1/2. And we can easily factor this a out, right, and get something that looks like this without the a. And this part right here is what we're going to focus on in this video. And anything that we say about this part, of course, at the end of the day, you could just multiply by a. So we're just going to focus on this. This is kind of the meat of what's going on here. So we will focus on this. Okay, and I'll just make the note what I just said. We can always just multiply by that constant a at the end, okay, to get the actual sum, right? So we're just going to focus on the part with the common ratio. Okay, so there is a geometric series is defined, like I said here. In the case of what I drew up here with this dot dot dot, it would be an infinite geometric series. It keeps going on forever. But we're actually going to start by looking at the finite case. So the finite geometric series. That's what we're going to look at right now. And what is that? That's just a sum where I'm going to start at 0, but I'm only going to go up to some number n. Okay, I'm not going to go all the way to infinity. And we're going to have our common ratio r raised to the k. Right? That's how I express this in this summation notation. Okay, but it's finite. Okay, so it stops when I get to n. Right? It stops when k equals n. So what does this look like? It's just 1 plus r squared plus dot 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 plus all the way to r to the n. Okay, so this is a sum. There's only finitely many terms, so it equals some number. I'm going to call that number s just for convenience, so I'll write it out one more time. So s is the sum we're looking for, and it looks like this. Okay, and we want to try and have a nicer expression for this, a shorter expression that doesn't have these n terms in it, some compact expression that equals the same number s that we're looking for. So remember, each term is just r times the previous term. So what could I do to s to make it look sort of like itself? And then the idea being that maybe I can subtract this new number I get from s, okay, and end up with a much simpler expression. Okay, so what should I do? Well, each subsequent term is the previous times r. What happens if I just multiply the entire sum s by r? Okay, what happens there? Well, I'm going to have 1 times r, okay, and I'll write it sort of suggestively, implying what we're going to do next. I'm actually going to write that underneath the r above. So we have 1 times r is r, and then we have r times r is r squared. R squared times r is r cubed times r is r to the 4th, and so on. R to the n minus 1, the term before the last one up here, times r would be r to the n. Okay, and then we have r to the n times r, which is r to the n plus 1. Okay, so this is r times s. Now what can we do here? Well, you can see the way I wrote it, all of these terms are the same. So if I take s and I subtract r times s from it, what am I going to get? I'm going to get 1 from the s term, and then I'm going to get r minus r squared minus r squared, and so on. All those cancel until at the end of the day, I'm going to get 0 minus r to the n plus 1. So there we go. So this expression now just has 2 terms in it. And on the left side, I can even factor out an s, okay, to get 1 minus r times s. And remember, s was our sum. This is what we were going for at the end of the day. Okay, so what do we want to do? Well, obviously, we would love to divide both sides by 1 minus r. Okay, that's what we would love to do. But we can't always do that. What if 1 minus r is 0? Then I can't divide by it, right? Okay, and when would 1 minus r be 0? It'd be at 0 if r equals 1, right? And so if r equals 1, this side would be 0, this side would be 0. Okay, but our sum definitely isn't 0. Right? Our sum is just adding up 1 to the 0, that's 1, plus 1 squared, right? It's just going to add up 1 all these different times. So we're actually going to have 2 different cases. Okay, so the first case is if r does not equal 1, then I'm free to divide by 1 minus r, and I get this really nice expression, 1 minus r to the n plus 1 over 1 minus r. But then we have to also consider what happens when r actually equals 1, and then we don't have to go through all this business. We can just go back to the beginning and say, oh, I'm just adding up 1 all these different times. Well, how many terms are there here? Well, this is like r to the 0, r to the 1, all the way up to r to the n, so there's actually n plus 1 terms. Okay, there's n plus 1 terms in that sum. Okay, because this is n, and then there's 1 more. Okay, so we would just get 1 added up that many times, and we get n plus 1. Okay, so there you go. So that is a finite geometric series, and more generally, I'll just write this also. Okay, more generally, what happens if I have a sum, and what if I don't want to start at 0? What if I want to go from m up to n, r to the k? Well, the exact same technique, everything we did is the exact same. We just start here with r to the m and then go all the way up to r to the n. All of the work would be the exact same, and what you get is just instead of this 1 here, right, instead of this 1 for our first term that was r to the 0, our first term here is actually r to the m. So we're going to get r to the m minus r to the n plus 1 over 1 minus r. That's when r does not equal 1. And then when r does equal 1, we're just adding up 1 this many times. How many times is that? Well, it's n minus m, but then we have to account for that 1 extra term, right? N minus m is all the terms starting at m plus 1 and going to n, but we also have this m term. Just like up here, we have these n terms starting from 1 going to n, but we also have our first term, and that's why we had n plus 1. It's the exact same here. We're going to have n minus m plus 1. You can just count those. Okay, and you get n minus m plus 1, and that's when r equals 1. Okay, so that is the general form for a finite geometric series, and that's great. Okay, what about infinite, though? Okay, what about the infinite geometric series? And that is where I have a sum, and again, we'll just start with k equals 0, and it's going all the way to infinity this time. Okay, so I have r to the k, and I'm adding it up 0 to infinity. Okay, this is an infinite sum. What's the definition of an infinite sum? Well, it's just the limit of all the partial sums. So it's the limit as n goes to infinity of these partial sums, starting from k equals 0 going up to n. We have r to the k. Okay, and that's nice because we already figured out what this is, right? We already figured out what that is before. So I'll just stick that in there for now. So we have the limit as n goes to infinity of this. Again, there are two cases. Can't get around that. So it's 1 minus r to the n plus 1 over 1 minus r. This is when r does not equal 1. Okay, and we have n plus 1 when r does equal 1. Okay, so since this is an infinite sum, we got to think about the question of whether this sum converges or not. Okay, so down here, so we're taking the limit as n goes to infinity in both these cases. In this case, right, as n goes to infinity, this just keeps getting larger and larger, right? We're adding up 1 just infinitely many times. Well, that doesn't converge. That goes to infinity, right? Okay, so we definitely don't have convergence of this sum when r equals 1. What about when r equals negative 1? Okay, what about when r equals negative 1? We could think about, right, you can think about what this sum's doing. When k is 0, we're just going to get 1. Okay, then we're going to add to that. When k equals 1, we're going to add to it negative 1. So what are we really getting? Well, we're going to have 1, okay? Our next term is, our next value in this sequence, right, if we start adding up from 0 to n. If I just add up the first term, it'd be 1. And then the second term would be 1 minus 1, right? 1 plus negative 1, well, that's 0. The next term would be 1 minus 1 plus 1, well, that's 1. Okay, not the next term, sorry, the next partial sum. Okay, and the next one would be 1 minus 1 plus 1 minus 1, well, that's 0 again. Okay, so all of these sums for different values of n, as n increasing, they're just alternating between 1, 0, 1, 0, 1, 0. Okay, I just am either adding or subtracting 1 with each subsequent term, so I'm just going to alternate between 1 and 0. Well, that doesn't converge either. That doesn't get closer and closer to any one particular value. Okay, that just flip-flops back and forth between 1 and 0. So that doesn't converge either. That was when r equals negative 1. Okay, what about when the absolute value of r is greater than 1? Okay, like what if r was 2? Okay, well then you can see I'm just adding up larger and larger powers of 2. That's going to go to infinity as well. And you can even see it from this expression right here. Right, if the absolute value of r is greater than 1, let's look at this term as n goes to infinity. Right, if r is positive, that's just going to start blowing up. Okay, so this whole sum is not going to converge to anything. Okay, and if r is negative, then this is going to be getting larger and larger in magnitude with each subsequent power. And it's just going to be flip-flopping between being positive, negative, but growing all the time. Okay, so that's not going to converge either. So all in all, okay, by whatever way you want to think about it, this does not converge if the magnitude of r is greater than or equal to 1. Okay, we just went through all those cases. Definitely doesn't converge there. But what about if the magnitude of r is less than 1? Okay, what if the magnitude of r is less than 1? Well, then this term right here, which is the only part of this expression that depends on n, that term right there is just going to keep getting smaller and smaller. Okay, and actually that term is going to go to 0. It's going to converge to 0, okay, as n goes to infinity. And so in the limit, this term is going to go away, and what am I going to be left with? I'm just going to be left with 1 over 1 minus r. Okay, and again, I'll just make another note. That is if the magnitude of r is less than 1. Okay, so this is the classic sort of infinite geometric series formula that you've probably seen somewhere in class in some context. If you haven't yet, you definitely will at some point, I'm sure. Okay, so that's what we get. And that is only if the magnitude of r is less than 1. If the magnitude of r is greater than or equal to 1, that sum does not converge. And I'll just make this note again more generally. Okay, as long as we have this condition, the magnitude of r is less than 1, then I can start this infinite series sum. Right, I don't have to start it at 0. I can start it at m, r to the k, and what I get, using the exact same technique as what we just did, just plugging in this expression instead of this one, right? But all the logic is the same. Then we end up with r to the m over 1 minus r. Okay, so this is like, what if m was 2? What if I started this infinite geometric series at 2? Then I would just have r squared over 1 minus r. And people remember this by sort of saying to themselves, this infinite geometric series, that sum is just the first term over 1 minus the common ratio. That's what you'll hear people say. Okay, it's the first term, right? The term where I plug in the smallest value of k, the first term, r to the n, over 1 minus that common ratio, r. Okay, so that is the infinite geometric series. That's where that formula comes from. Okay, so this is really useful. I'm sure you'll see this at some point. Okay, and there's many series that are related to this one, but I'll just give you one, a related series. Okay, and this is again, as long as the magnitude of r is less than 1. What if we look at this series instead? It's going to be not the geometric series, but it's related to it. We're going to have r to the k, but now each of those r to the k terms we're going to multiply by k, actually. Okay, so this geometric series, this part is the same as before, but now we've stuck a k in there. Is there any way to figure out what this sum is using what we've already done? Well, what can we do? Well, look at this inner part. Right? Doesn't that sort of remind you of taking the derivative of r to the k? If I differentiate r to the k, I get k r to the k minus 1, right? Well, this is pretty close. How can I make those summands look more like this? I can just factor out an r, right? I'll just pull one of those r's outside. I get r times this sum, right? K times r to the k minus 1. I took one of the r's outside. Now that looks exactly like our derivative, so I'll express it in that form. This is just the derivative with respect to r of r to the k. Okay. Now what I'm going to do is take that differentiation outside the sum. Okay, that's something you can't always do, but it turns out in this case we're allowed to do it. Okay, so you can take my word on that. So I'm going to do it here. So I take the derivative outside the sum. Okay, and this is what I'm left with. And now this looks almost the same as our geometric series, right? Right, almost the same as what we had up here. Right, but this started at 0, and the one we have down here starts at 1. Okay, but that's fine, because I'm taking the derivative of it, right? So if I add a constant to this sum and take the derivative, that constant will just go away. It'll just become 0. And what constant do I want to add? Well, I just want to add the first term back in, which is r to the 0, which is 1. Okay, so these two are actually the same, right? Because all I've done is add 1 to this expression, but I'm differentiating. Okay, so when I differentiate 1, I still end up with 0, so that's totally fine. And now that's our geometric series. So this is just r times the derivative. What was this? It's the first term over 1 minus the common ratio. The first term is r to the 0. That's 1 over 1 minus r. Okay, and now I just have to take that derivative. Well, that's just the derivative of 1 minus r to the negative 1. Okay, so the negative 1 comes down, it becomes a negative 2. And then with the chain rule, you have to remember to multiply by the derivative of the inside, which is going to give me an extra negative 1 that cancels that one. And what I end up with is just 1 minus r squared. Okay, so the end result here is r over 1 minus r squared. Okay, so this is another useful series. Okay, you'll see this one come up quite a bit as well, and we actually can get a nice clean expression for it using the geometric series formula we already derived. Okay, so that is all I had to say about that, but let's look at a couple more examples. Let's look at some examples of putting all of these equations into action. Okay, a couple examples. So let's start with the one that we began this video with, 1/3 plus a 6th plus a 12th plus a 24th, and so on, an infinite geometric series. Okay, so what I'm going to do is what I said before. I'm going to factor out that coefficient of 1/3, and what I'm left with is just 1 plus a half plus a 4th plus an 8th, right, and so on. Each term is just 1/2 times the previous term, and so this is just 1/3 times this geometric series. Look at that. It's just 1/2 raised to the k. Right? Each time I just keep multiplying by 1/2. So we know what that is. That's 1/3 times the first term, 1, over 1 minus the common ratio. Okay, so that's 1/3 times 1 over a half. That's just 1/3 times 2, so we get 2/3. Okay, so that's the first example. Next example. Okay, what if I have this sum? I'm going to start at 3 now. I'm going to go to 30. There's going to be a lot of 3's in this one. I'm going to have 3 to the negative 3k. Okay, so at first glance you might say, wait a second, this isn't something raised to the k, it's raised to the 3k. How are we going to use a geometric series here? Well, that's totally fine. That's totally fine, right? Because like 3 raised to the x times y is just 3 to the x to the y, right? Those are some exponent rules. Okay, so what do we have here? This is going to be the sum when k equals 3 all the way up to 30 of what? Well, I'm going to take the negative k outside as my y, and what I'm left with is just 3 to the 3. Or actually, I'm going to just take k out, right? Because in the geometric series, right, we just want our k to be alone there. So I want to figure out what my r is. So I'm going to take k outside, and what am I left with? I'm left with negative 3. So we're going to have 3 to the negative 3 to the k. Okay, 3 to the negative 3 to the k. And that's good because now 3 to the negative 3, that's just 1 over 3 cubed, which is 1 over 27 to the k. And 1 over 27, okay, that is now our common ratio. We can see each term is just 1 over 27 times the previous term. So we can use our finite geometric series formula for this. Okay, and I'll tell you what it is. You can, of course, go back in the video to see it for yourself. Okay, but it's just the first term, 1 over 27 cubed, minus not the last term, but actually one more than the last term, right? Remember how we proved that? We multiplied by the common ratio, and we had that extra term, r to the n plus 1, that we subtracted. So we're going to have 1 over 27 to the 31, not the 30, all over 1 minus 1 over 27. Okay, 1 minus 1 over 27, that's just 26 over 27. When I divide by it, I'm multiplying the top by 27 over 26. That 27 is going to cancel one of these 27s in each of the denominators. So what I end up with is 1 over 26 times 1 over 27 to the 1 over 27 squared minus 1 over 27 to the 30th. Okay, and I'll just clean this up a little bit more. So this is 1 over 26 times 27 squared times 1 minus 1 over 27 to the 28. Okay, so we have 26, 27, and 28. That's kind of cool. Okay, so there you go. So that's your answer. That's what that finite geometric series sums to. Okay, and one last example, just to use that other related series we saw. So it's the sum k equals 2 to infinity of k over 2 to the 2k. Okay, so this one has a lot of 2's in it. Maybe I should have made this the second example and this the third example. Oh well. Okay, so we have a sum of k over 2 to the 2k. What can we do? Well, we're going to use that same trick, right, where we're going to have our k, and now this 2 to the 2k, we're going to re-express that, right? We're going to do this same thing. All right, we're going to do the 2 squared, which is 4, and that is going to be raised to the k. So we have k times 1/4 to the k. Okay, and that looks almost like our series that we saw before, but this started at 1. Right, this was the sum of k times r to the k, but k started at 1. So what can we do? Well, that's fine. We're only off by one term. We'll just write down what we want it to be. And then we'll subtract off the thing we added, which was the term where k equals 1. And when you plug in k equals 1, you just get a 4th. Okay, so it's this whole sum minus the first term, which is just a 4th. Okay, and what was the sum? It was the common ratio, okay, over 1 minus the common ratio squared. It was the common ratio over 1 minus the common ratio squared. Okay, so we have 1/4 over 1 minus 1/4 squared minus 1/4. Okay, so what do we get? Well, this is just 3/4 squared. Okay, one of those fourths is going to cancel here. This is going to be 1 over 9 over 4, which is just 4/9. And then we minus a 4th. Okay, and this is going to be well, 9 times 4 is 36. This is going to be 16 36 minus 9 36, which gives us 7 36. Okay. All right, so those were 3 examples using each of the topics we went over. Hopefully this makes things a little more clear, and I'm telling you, I definitely think you will see at least some of these series at some point in your studies. So hopefully this will be helpful. That's all I had for this video. I will see you in the next one.